So, let us start with the new layer of the TCP/IP protocol suite. We have already studied about the data link layer for the OSI model, and because data link layer is mostly service oriented layer, so we studied that for the OSI model. Coming to the IP layer or the network layer, we studied both for the OSI as well as for the TCP/IP. In OSI, we studied all about the routing algorithms, how they function, and coming to the TCP/IP, we studied about the designing, how the IP is designed along with all its modules, the components, and how the addressing is being done, the logical addresses, how subnetting is being done. So, that is all about your IP layer or the networking part of the TCP/IP protocol suite. Now, coming to the next layer, means the higher layer of the IP or the network layer in both the models, that is OSI and the TCP/IP. The next layer that is upper to the network layer is the transport layer, right. In OSI model, the transport layer, the layer works similarly in the similar way for both the OSI and the TCP/IP, but because OSI is a service oriented, so that is included when you study about the designing of the protocols in the TCP/IP. So, we will more focus on the TCP/IP model, where you study about the protocols, and including within the protocol itself you study the services, which is also a part of your OSI model. So, what we will do, transport layer for the TCP/IP protocol suite, TCP/IP model you can say. And we have already studied for the TCP/IP model, the transport layer has got two kind of services. One is the connectionless and another is the connection oriented. And because two kind of services are supported in this layer, so definitely you will have two different protocols for each kind of services. So, for the connectionless service, you have a protocol in the transport layer, that is the user datagram protocol or the UDP. And for the connection oriented service, you have a transmission control protocol, that is called TCP. So, we will study both of these two protocols for the TCP/IP model for the transport layer, but first we will cover the UDP. You know, this is a connectionless model. The first characteristics of connectionless service, meaning when you talk about the connectionless, it is definitely having a reliable protocol, right. So, it is a less reliable protocol. So, when you talk about the connectionless protocol, definitely this is a less reliable or unreliable protocol in comparison to the TCP/IP. Then why you study about this UDP then again? Because the first property it is simple and very easy to study and give the exam. That is what is your UDP protocol characteristics. Now, before going to the protocol, we will study some of the common things that is possible for the transport, that is actually related to the transport layer. Why a transport layer is required? Till now we have studied about the routing, about the framing, data comes from the upper layer being framed into a IP packet or a datagram, again encapsulated into a frame, being transmitted, decapsulated, and it is delivered to the host. That is what we studied. When we studied about the routing, we studied that the source starts the packet and it delivers to the destination. The job is over. Why you study the transport layer again? This is what is your host to host delivery, right, or host to host communication. Identifying a host in a bigger network, deliver the packet to the host. Then again, what is the role of the transport layer then? Application to application. Then what the application layer will do? Let us talk about a host, a sender host, and you have a destination host. Now, if I use the IP, any routing algorithm, my packet will be delivered from this to this, I understand. Now, let us say this sender has to go, a host has got multiple processes. You know what is a process? What is a process? I was expecting this definition. A program in execution is a process, right? Any active program is a process. Fine, let us agree to that. We are not going to more detail about the process. Now, let us say I have 3 processes running in my host. This process sends a mail, this process sends a query, and this process does something else XYZ. And here is the destination, or let us say I will say this is the server, I will say this is a client and this I will say as a server. The destination is a server. Now the mail comes to this IP, goes all the way from the source to the destination, and now it goes to the destination delivered to the host. Clear? And now the host delivers the mail to a process which was expected to give the answer to this query. And the query was submitted to a host who was expecting a mail. Is that okay? Not okay. Because a mail process will expect definitely a response from this mail process, and a query process will definitely expect a answer from the process. That means any host having multiple process, you know that multitasking, multiprogramming, everything. So any host is expected to do n number of processes at any time, and a single host having multiple processes should expect the corresponding data to be processed accordingly. That means a peer-to-peer or process-to-process communication is required. Other than the host-to-host delivery, it is required that in the host, the corresponding process must be delivered the packet or the data. That is what is the responsibility of the transport layer. Either it is a connection-less service or it is a connection-oriented service, does not matter. What matters is the process-to-process communication has to be done by the transport layer. Right? Now let us expect you have a process here. I am talking about the process now. You did some client service programming, right? At the initial in the lab class you did something, the client server programming. What you did in the program? Can anybody answer me? What you did with the client server? How it actually worked? Client is a process. You generated or created a process, that is a client process, and that client process sends some message to a server process in another host, maybe in the even same host. We are talking about in a different host. So now the server process, what it does? It sends back a reply to the client process. So how this process is again identified? A host is identified with an IP address, logical address, and then the physical ID, the MAC ID. But when coming to a host, you have multiple processes. How the process is identified? It has a process ID, I agree, this is a process ID. Each process has got an process ID, or that is called a port. That means to access a process in a host, you need to access actually the port number of that host. The port number has to be opened to access this process, and then only the data could be sent or retrieved from that process. So every process in either a client or a server needs to be identified with a unique ID, or you can say a number, not unique ID exactly, with an identification called the port number. And once the port number is accepted or it is open or active, then the process-to-process communication takes place. Right? Now, how these port numbers are identified and how a port number is known for a client process and how a port number is identified for a server process, and who manages all these port numbers, who generates it. Let us say in the client side a process is created. As soon as the process is created, it requests the operating system to assign a number, and that number is your port number. If this is a client process, the port number could be random. A port number could be random, and usually that ranges from 0 to a 16-bit number, so it ranges something between this 2 to the power 16, right. It could be any number between 0 to this, and these random numbers generated by the OS for the client process are called the ephemeral port number. Is called the ephemeral port number. So that is called the ephemeral port number, right. Now let us say the client opens a process which is a daytime process, or let us say an SNMP message, any message. Let us say the client wants the day and time from the server. So when this process is generated, it requests the OS, and let us say it gets a number 15,000. It gets a number 15,000 randomly assigned, right. Now, when the corresponding daytime process has to be created or to be accessed at the server side, if this is the client and the process is daytime, definitely at the server side also this has to be open daytime, otherwise it will give you a different result, right. So, now at the server side, if again a number is randomly generated, then what will happen? Definitely the process cannot communicate with the expected result to the client. So, to have the corresponding service from the server, the processes that are identified in the server side are called the well known port numbers, and they have the fixed number. Let us say daytime, meaning here the daytime will be open and its fixed number is 13. So, client side, when an ephemeral port number is generated, it can be random, but when it comes to the server side and the same process has to be opened, it has to be opened with a fixed number that is already stored in the server, and that is called a set of well known port numbers are there, out of which the corresponding service or the port will be opened and the server can reply back. You must have seen in the client server program, if you give a port number or any process of the client side, this process must be same in the server side, otherwise you do not get the communication between client and the server. So, you have a set of ephemeral port number which is random, and corresponding to that you have a set of well known port number which is fixed. That is how a client and a server communicates with each other in the transport layer. Now, when this communication takes place, have you used any specific address called the socket address? Have you used that? What is that? What is the format of a socket address? IP address? So, you have two set of addresses, IP followed by the port number. So, the client side, if you say this client IP address and this is the ephemeral IP address, this will be something, let us say x dot y dot z dot something, and this will be 15,000. This is the socket address for the client. That means to identify a process, you have to identify the IP of the host, that is the destination IP you can say. Here also you have a set IP address followed by a port, and this port is the well known port number. So, a port in this IP will communicate with the port in this IP. So, always they work in a pair, the IP address along with the port address, and combining these two we say that is a socket address. So, for process to process communication in the transport layer, you always use a socket address other than the physical or the logical addresses, and that contains the port addresses of a process which actually does the communication with the corresponding process. This is how the process to process communication takes place either for UDP or TCP, does not matter, but this is the principle of communication in the transport layer, right. Now, coming to the UDP, now it becomes different. I mean, we have to distinguish between the operation of UDP and the TCP, how they work. They work on the similar principle of socket address and all, but how they are different again. So, first we will study about the UDP datagram format. As you know, any data contains a data along with a header. We have studied this earlier. So, the UDP datagram, it has a fixed header size, very small to remember, having only 8 bytes. This header is of 8 bytes, right. This is the source port address, this is the destination port address, this is the total length, and this is a checksum. So, all 16 bit. Now, as we discuss the source port address, because so this is 16 bit means definitely the port number could be 0 to again, it ranges from 0 to 65, 535, 64 KB you can say kilobits, right. So, any number between that. So, when it is working, when the host is working as a client, the source port number becomes your, when it works as a client, the source port becomes ephemeral and destination becomes your well known, and it is the reverse when this works as a server. Your source becomes the well known and the client becomes the destination becomes the ephemeral port. That is how they communicate. And the port, all these port things we studied about is okay. Now coming to the next field is the T length field, the total length field. What is the total length field? The total length field of the UDP datagram. That means it contains the header plus the data, right. If you remember, there was a field in the T length field in the IP datagram, right. What it says? The total length of the IP datagram. So, your this says the IP T length. Now, let's say that equal to 1000 in the IP header. I am talking about the IP header. Let us continue. Let us say in your field you have the T length field, and this T length says your header plus the data, right. Let us say your data field is not there, only the header field has to be there, and this is because again this is equal to 16 bit, that means total length could be 16 again, that 64 535 in terms of bytes I am saying, okay. This could be the length of the UDP datagram, and the minimum could be 8 byte, the maximum could be this, the minimum could be this. Reason is that when there is no data, when there is no data only you have the header field, 4 header, right. But when the data is added, you will have 8 plus data. Your header is always 8, whatever will the data field will be the total T length, but if there is no data, only the header is passing, so you have the minimum 8 byte with no data. Now, why I am saying this T length? Because if you go for the next layer, that is the IP layer, you have a T length field. What this T length says? The total IP, I mean the header plus the data, and in the header there is a field H length, if you remember, there is a field H length. So, now you subtract the whole T length minus H length, what will be the data field? Will be the data in which layer? IP layer. Now, this data equal to what? Is this whole thing? That means the T length of the UDP datagram is equal to the T length minus H length of the IP datagram. Agree? The calculation is very simple. In the IP you have a total length, you have a header length, subtract the total length minus the header length, you get the data, and that data is nothing but the data you get from the upper layer, that is the UDP, let us say UDP transport layer, and that is equal to again header plus data, and header is fixed. So, this T length is how much? 8 plus data. So, if you calculate, if you get this one minus 8, you get the actual data size, right. H length in the IP is variable, that ranges from 20 to 60, you know that. H length in IP is variable 20 to 60. If you know that, then you can get the data size, and this data size is nothing but your T length of your UDP. You subtract 8 byte from that, that is your header, you get the actual data. Very simple case. So, then why you add in this field here? Even from the IP layer also you can calculate what is the actual size of data. So, why an extra field is added here? We always know that the communication is a peer-to-peer communication, right. That means UDP or the transport layer will always talk with the transport layer. If you don't mention the T length here, then what the receiver will do, it will ask its lower layer, that is the IP, because IP is already decapsulated. So, what it sends is only the data plus this. So, it has to ask the IP layer, the lower layer, about the size of the data. That means another communication will be required in this, which is an overhead. So, instead of bothering the other layer to ask about the size of the data, the transport layer itself gives a data of T length, so that the corresponding layer can know what is the size of data from the transport layer of the sender. Otherwise, you can easily calculate. Being any designer, you can calculate what is the data and what is the T lane, what is the H lane, size of the data minus the header is the actual data size. That is okay. But when the transport layer of the receiver talks, he has to query about the IP layer or the lower layer to know the size of the data, which is an overhead. To avoid that, you have a T lane, field in the header information of your datagram, UDP datagram, and then you have the checksum. And you know what is the role of the checksum, why the checksum is used? Checksum is used for your error checking, right. This is what is the header or the UDP datagram header, very simple and the easiest one you can remember. Okay. Now, when the UDP functions, what are the different operations of UDP or how the UDP operates or the services of UDP you can say. I will talk about the UDP operation. The first kind of operation is connectionless service. It supports connectionless service, meaning if you have a single source and a single destination, all the datagrams to be generated in the source are destined for this destination. Let us say 5 number of datagrams are created or 5 packets are created for the same from the same source towards the same destination. But then also because it is a connectionless, all the 5 packets may follow different paths. What would happen if it is a connection oriented? A dedicated path would have been established, all the 5 packets would have been followed the same path, delivered, then disconnected. That is the principle of connection oriented. But coming to the connectionless, the source remains same, the destination remains same, but if the packets are multiple, they may follow different paths depending on the network scenario. That is the principle of your connectionless service. In this case, by doing so, your reliability is reduced. That is one of the principle of your connectionless service. Another is, you know what is a stream data service? You do a lot of data downloading, you know, streaming all those things. What is that? Streaming of the data, what is that? You do that, but never try to understand, right? What is stream data service? Anyone? When the data is generated, it is delivered to the layer. Let us say, let us talk about this transport layer. We are not talking about the application layer. Let us do the transport layer. When the data is generated, it goes to the transport layer byte by byte. It goes to the transport layer byte by byte. Streaming, continuously the data goes, and the transport layer chunks the data into smaller sections, or you can say the segments, and then each segment is again added into the header or encapsulated into the header, and they are being transmitted as we talk about. That is what is stream data service. But UDP does not support stream data service. No stream data service. For UDP it is no. Meaning what? If you have a large data to be generated by the application layer, you cannot have a UDP and your transport layer. So, UDP only supports when you have a short messages or short data that could be encapsulated into an UDP datagram. If your UDP datagram is 1 KB size, then minus this 8 byte and all those, or the 16 byte of all those, whatever will be there, if that encapsulated into this portion of the data portion, then only the UDP will work, otherwise not. So, no stream data service is possible in the UDP, but in case of TCP this is possible. TCP is a stream data service. So, whenever you are using any protocol, you are saying the transport layer protocol is TCP or UDP, make sure if you are saying TCP, that means first of all you are going for connection oriented, that is fine. But in the connection oriented, you are also going for the streaming of the data. But UDP does not have any stream data. one whole data will be generated, that will be encapsulated into the UDP datagram, and then the rest of the things takes place. That is what happens in the UDP protocol, right. So, that is what is your connection less service. Then another is your next operation is flow control, flow and error control. You know this two very nicely. UDP does not support any flow control. UDP supports no flow control. That means if any receiver is overloaded with the packets or datagrams, simply the packets are dropped, nothing to do, no flow control. So, no windowing, you know the sliding window, all those, they never work here. No stop and wait, no windowing, packets transmitted, if overflow, dropped, lost. That is what is no flow control. And for error control, only little bit of error control is being done by the UDP. What are the error control mechanisms? You know that ARQ, you have a lost data, you have an acknowledgement, positive acknowledgement, negative acknowledgement, then timeout, retransmission, many features are there combined into one ARQ, right. So, for UDP, what it has is only a checksum field, you know that. So, what it does, it calculates the checksum, and if it finds any error, the only thing is that it detects the error. How it detects? By the checksum method. If it finds any error, then it simply drops the packet. That is all what it can do. So, no negative, no positive acknowledgement, no timeout, no retransmission, no duplicate discard, nothing. Just little bit of flow error control, calculates the checksum, if finds an error, drop the packet. That is what is being supported by UDP, no flow control and a little bit of your error control mechanism. Then the third operation is encapsulation and decapsulation. This we all know. Let us say a process is generated. When the process is generated, it goes to the next layer. That means it is encapsulated into the, let us say process P1, it is encapsulated in the transport layer with the header. Then this is again encapsulated in the lower layer, that is in the IP layer. Now this becomes the data and added with the new header. Again this encapsulated with the new data. Now this becomes the data and with the header information. So your process here encapsulated, again encapsulated with some header, again encapsulated with some header, right. Then it goes to the all over the file layer, then it reaches to the DLL, or this is again the data link layer, you can say. It goes here, so with header and the data. Then coming to the next layer, when it goes to the next layer, it goes here with this much, where you have the data and you have the header, and when it goes here to the corresponding, this is again the IP layer, corresponding IP layer. When it goes here, you have the again the data here and the header here, and finally it is decapsulated and goes to the destination process. The P1 comes here. That is what is your encapsulation and decapsulation, starting from the generation of the process all the way from the different layers coming to the next and coming to the upper layer delivered here. That is what is the service, the encapsulation and the decapsulation of the data, right. Actually these are the services we know, but they are again characterized, or you can say they are again distinguished by the protocol designing for more clarity. Then the next kind of service is queuing. Whenever a process is generated, it sends a request to the OS, and we know that a port number is generated, right. Along with the port number, two queues are generated. One is the outgoing queue, another is the incoming queue. If this is outgoing, this is incoming. Whenever the process is generated, along with the process, two queues are generated, one is the outgoing, another is the incoming. In some systems even only one incoming is okay, outgoing they are understood that they will go through. But some processes, when it is a slow processor, we assume that it may not go through, so it has to wait for a time, so a queue can be generated. And then you have the UDP process or the UDP datagram who process it and does the rest of the things, right. So, when a process is created, it may happen that the same process or the same host may create multiple processes, right. So, when multiple processes are created, where they will go? They go to the outgoing queue and being stored there. If the UDP is not smart enough to process at a time, and when the UDP is free, it takes the process from this and does the encapsulation, decapsulation and send it to the destination. Similarly, at the receiver side, when the UDP receives the packet or the UDP datagram, it goes on entering into the incoming queue, and then the processes are delivered to the corresponding, or the packets are delivered to the corresponding process. Like this host sends 3 processes, P1, P2 and P3. One is again, as I said, one mail, let us say one mail, there was a query and there was one request, any kind of, let us say connection request or something. And all of them were maybe for a same destination, maybe for a different destination, but they are all generated by the same process, I mean the same host. So, what they do? All these processes they enter into the same queue and being processed by the UDP. That is why you have, along with every queue, along with every process, you have queues generated automatically by the OS. And whenever the process is terminated, then the queue is automatically destroyed with it. So, port generated, along with that you have the process generated, I mean the queue generated, port is over, I mean the terminated, queues are destroyed. That is what is the queuing job. And another is a multiplexing and demultiplexing. Have you ever received any message like port unreachable message? Has anybody received? What is that port unreachable message? Let us say you have 3 ports here and these 3 ports are connected, I mean single host, multiple processes are created and there is only one UDP. And the job of the UDP is to encapsulate and decapsulate, so he has to do all the job. So, this is again many to one structure, right. Then it goes all the way from the other part. So, when multiple processes are there and the same UDP, what it does, it multiplex them and sends the packet accordingly. The receiver side also, now it has to demultiplex. This is demux, I mean the again UDP, that demultiplex, it goes there. Let us say same process, it has to be delivered to different, I mean same packet, it has to deliver to different processes and it does by the demultiplexing. Now, let us say a packet comes with a process number 1000. When it comes here, the UDP checks that the process or the process those are the active does not have the number 1000. That means a port which is a 1000 belongs to a 1000 number is not active now. So, in that case what it does, the UDP tells to the ICMP message. Did I say about this ICMP message? It is in the IP layer. Along with ARP and RARP, you have another protocol, that is ICMP, Internet Control Message Protocol. It says to the ICMP that send a port unreachable message. So, whenever you get a port unreachable message means your port is not active or it has been destroyed or it has been closed. If the port is active, it is delivered there. If it is not active, it says that port unreachable message. ICMP, who sends this? ICMP protocol sends it and this ICMP gets a message from the upper layer, that is UDP. UDP says to the ICMP that you send a port unreachable message to the sender who has sent this packet. Then again it has to be destroyed or the rest of the things will be taken care of. So, these are the different operations of your UDP. The connectionless service, how it works with connectionless, how it supports, does it support the stream data or not, then how it supports the flow control, the error control, and then you have the encapsulation, decapsulation, how the multiplexing, demultiplexing takes place, how the different queues are generated and the queues are operated in the UDP. These are all about the UDP operations.